Hi! So this is a short video about the counting unit in chemistry, which is called the mole. We're going to look at what it is, what it means, what the number is, and how do we use it in chemistry. And we're going to use it a whole lot after today. So let's take a look at finding molar mass. So the mole is the counting unit, as I mentioned, for chemistry. And it's a number. It's a word that means a number, just like dozen means 12, or like ream of paper is like 500 sheets, or a baker's dozen means 13, or a gross of something is 144 of something. Except the mole, the number is a little bit bigger. The mole is 1 mole is equal to 6.02 times 10 to the 23rd of something. So 6.02 and then 21 zeros after that. To get to 1 mole. It's a very, very large number, larger than anything you could comprehend, larger than the fastest supercomputer could count in a million years. It's an extremely, extremely large number. And it's named, sometimes called Avogadro's number. That's the person who's responsible for determining what the number is. But we use that as the counting unit in chemistry, obviously, because the atoms and molecules are very, very small. So even a ginormous number like this would be well represented by things you can see and do in chemistry class because the atoms are very, very, very small. But it's our counting unit, and we're going to use it to count. Each element is different, kind of like if I said you had, let's say, a dozen eggs and a dozen donuts. What do they have in common? Well, the number is 12, right? So if I had 1 mole of sodium and 1 mole of chlorine, they both would be the same number of atoms, 6.02 times 10 to the 23rd atoms, but they wouldn't weigh the same. Donuts and, what did I say? Donuts and eggs? I don't remember. Donuts and eggs are not the same thing. So even if you had a dozen of each of them, they would not weigh the same thing. Same with elements. If you have 1 mole of sodium and 1 mole of chlorine, those two things don't weigh the same amount because there's different pieces that make up sodium and there's different pieces that make up chlorine, okay? So each element has its own unique molar mass, which is also known as the mass in grams of 1 mole of that element. And guess what? You can find it on the periodic table. It's very, very easy to do. I picked neon here, right down there at the bottom of the periodic table. That number, we previously talked about that number as like the atomic mass units, which is true. It is, but it has two meanings. So one meaning is that one atom of neon, one single atom of neon, weighs 20.180 AMUs, which is a very small number. You can convert it to grams. But that's not very important. Obviously, it's not going to weigh a lot, right? It's a one single atom. But if you took 6.02 times 10 to the 23rd atoms of neon, so 1 mole of neon, then that number, the 20.180, that would be the same it would weigh in grams. So this is also known as the molar mass in grams. And in fact, that's why we'll use it more often than not. So the molar mass in grams is the molar amount of 1 mole of that element. So if I took 6.02 times 10 to the 23rd atoms of neon and I put them on a scale, they would weigh 20.18 grams. And that's the number we're going to use pretty significantly in this class to be able to convert between grams and moles, because as you know, there's no scale that you can use to that will tell you moles, but there are plenty of scales that we use in class that are grams, and we'll be able to convert between them very easily. So any number in the periodic table, the bottom number, has two meanings, and from here on out, we're pretty much going to go with that's the molar mass. Sometimes they'll call it other things too, the molar weight, the formula weight. In this class, though, I usually just go with molar mass. So that's easy to calculate if it's obviously one element. If it's two elements, guess what? It's not rocket science. If we want to know the molar mass of, let's say, sodium chloride, well, it's just the individual elements added up to find the molar mass of that compound. So if the compound is sodium chloride, I'm just going to add up sodium and I'm going to add up chlorine, and then that's the molar mass of sodium chloride. So I set it up down here, and you can do it this way. So you would go look on the periodic table for sodium. You see that you can round them to the nearest tenth. So if you look at your periodic table, it's going to say 22.99 for sodium. Go ahead and call that one 23. But some of them, like let's say magnesium's like right in between. I think it is. I'm going to mess it up without a periodic table, but magnesium might be something like 24.3 something, or 24.299. Go ahead and round to the nearest tenth, so call it 24.3. Don't round the 3 down to 24. That will get you some calculation mistakes. So if it's in between, just round it to the nearest tenth. But a lot of them are very close to whole numbers, like sodium is 22.99. So if I want to find the molar mass like I was doing here of sodium chloride, I just add up 1 sodium and then also chlorine. Chlorine's also in the middle. I think on your periodic table it probably says 35.45. Just go ahead and call it 35.5. Don't round it down to 34. That would be too much rounding. So if you want to find the molar mass of sodium chloride, just add those two numbers up. I found both of these numbers in the periodic table right at the bottom in the same spot that I found that number right there. Let's go to each of those elements and I find the numbers directly on the periodic table. So of course, when you add them up, it equals 58.5 grams. So that means that if I wanted to measure out 1 mole of sodium chloride, I would take my table salt, which is sodium chloride, I put it on a balance, and I would add it until it's 58.5 grams. And then that amount is also equal to 6.02 times 10 to the 23rd atoms or molecules, in this case molecules, of sodium chloride. Okay? And if the formula becomes more complicated, like for example this barium fluoride right here, it's not more complicated, but you can clearly see it has a 2 there. So what we're doing, guess what? You just add 2 of them instead of 1 of them. So barium, you look on the periodic table, maybe even take a second to see if you can add them up before I do it. If you hit pause. I didn't know if you guys knew that, but you can actually pause these videos. Anyway, so barium on the periodic table is 100. Oh, there's all of them, shoot. 137.3 for barium. Again, don't round it. Fluorine, though, is like 19.0 something, so go ahead and call it 19. But there are 2 of them, so I multiply it by 2. Then I add those 2 things together for a grand total of 175.33 grams per mole. The label for molar mass is grams per mole. You're saying that's how many grams of that element equals 1 mole, or grams of that compound in this case. Here's the thing. Yeah, there you go. By now, I think you understand that the 2 there means 2 fluorines. If it's parentheses, guess what? It means you have 2 of everything in the parentheses, so it distributes twice. So you would have 1 lead, and then 2 nitrogens and 6 oxygens is 2 times 3 for the oxygens. So if you wanted to calculate the molar mass of lead nitrate, right here, lead nitrate, right there, lead nitrate, you would add up 1 lead, which is 207, nitrogen, 2 times 14, because there's 2 of them, and then oxygen is 6 times 16 again, because the 2 times 3 gets you to 6. So the molar mass of lead nitrate is 331 grams per mole. So a short primer on calculating molar mass. That's a thing we're going to do a whole bunch in the future of this class. Want to make sure that you knew how to do it, so when we come across it, you understand it and are able to do it without issue, or continue that next time I see you. Okay, this has been super fun. Everyone take it easy. Have a really good day. Be safe. Okay, miss you so much. Okay, bye.